Good morning, everybody. Congratulations, you made it for the last day of lecture. Right? Because next week is just test review, a non-lab. I always schedule that last lab to be a grasp type time, but homework is due for this Saturday. The astute among you will realize that there is no chapter 15 homework. Apparently that was on purpose. I had to look up what I did last semester to figure out what was going on. And indeed, I didn't give chapter 15 homework then either. So congratulations, chapter 14 homework is the last homework. And then we take the exam. I think that our test autopsy, the final exam time, is Tuesday of finals week. Whatever date that is, I don't know what date that is. Tuesday of finals week, that will be the only day that week that we meet, right? Always seems to be some confusion. We don't meet for lab, there's no lab practical, there's no lab final, none of that kind of stuff. Did anybody find the date? 14th. 14th? That sounds about right. Okay, so Tuesday 14th, 8 o'clock in here, not in the lab room. Okay? And I'll kind of give you more reminders of that. I've got the how to turn in your quiz sheet instructions going on up here. You can turn those in at the end of class. And then I posted an announcement for the fact that grass will open an hour late this Friday, and I won't be there. I've got to go get an injection in my back. Pump me up with steroids to calm down the angry nerves in my lumbar spine. So just if you need to get a hold of me, you were planning on coming in that Friday to beg for mercy, whatever it is you were going to do, reach out to me for email. We'll figure out a different time to be able to do that. Some of you are panicking right now. You realize the end of the semester is upon you, and what happens now, Mr. Bale? So please just email me. Some of you have emailed me saying, I'm not sure if I should even ask this. Just ask. You can't get without asking, right? Worst thing I could say is no, but just ask. You'd be surprised. The power that I have, so to speak. So, please just communicate if you're in any way worried, not sure what happens next, how to get what grades you want, blah, 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 blah. Those of you that have turned in quizzes, I should have your quiz scores already in there. I try to get those in there as fast as I can so that your grades are as up to date as possible. As of Saturday, really Monday morning, when I do sort of a final update of the homework scores, your grade will be basically everything except that last exam. Right? And you'll know, you go into Canvas and ask Canvas what you need to get whatever grade you want in the class. So again, any questions about any of that, let's try to have everything wrapped up by next week so that you don't need to ask those questions. So basically what should happen is you walk into the test autopsy, see your grade, and you know what grade is going to show up on your transcript. Right? Do that test autopsy and we'll be done. All right. So, the question probably is now in your mind, what am I doing here? Because if chapter 15, there's no homework, right? How can you possibly put I'll put the exam topics up later this morning, hopefully before noon. I've got all the topics written down. I just need to post the announcement, so it'll come up. And you'll see that on that, there will be no chapter 15 topics on the exam because I'm not giving you homework for it. So, why are you here? Well, the state of California does require that I cover topics, they just don't require that I test you on them, right? So I can run some little loopholes around. So the concepts you're learning about the laws of thermodynamics here, the first and second law, are ones that, for whatever reason, state of California, the MCAT, different licensing organizations, they don't come out of thin air. Their input is given in a lot of different areas, and thermodynamics is one of those areas they want you to know about. So there's a lot of behind the scenes going on. We were trying to tackle these different sort of thermodynamic processes, like what happens when you say keep the pressure constant in a system, and again, that system is that very specific, we've got the jug, we've got the container, right? it's got that movable piston in it, right, that can go up and down, and then we have that ideal gas inside. So as a structure, it's not a very useful one, like you really can't like use this for much in a practical engineering sense, but you can engineer things that behave so close to this, like a car's engine, for example, that these rules give predictive power for what's going to happen. And we're going to talk about your car's engine and air conditioners and things like that today, and how they're modeled after this. But, you know, how do we, you know, talk about what's going on in these like constant processes where we're holding one thing the same, but keeping everything else changing? If you've had chemistry before, you probably studied something called a PV diagram, or a pressure versus volume diagram. If you haven't, again, don't panic. It just means you haven't been poisoned by the knowledge of chemistry. So what we're going to do so I've broken the screen up into 4 different sections. And in each of these sections, we're going to hold one thing constant and see what happens to the pressure and volume specifically of this system right here, okay? So we'll start up here with the constant pressure process. And we're gonna try and figure out what it might look like visually, and then what that means for the first law of thermodynamics, where again, we have internal energy, we have heat, and we have work, okay? So constant pressure. What does constant pressure look like on a graph where pressure is measured along the y-axis? Got to kind of go back to your math a little bit, right? And I see some people out there doing it, right? It's going to look like a horizontal line, right? So the volume, let's think about this, right? Let's say we add some heat to this system, right? Well, gases, when they heat up, want to do what? They want to expand, don't they? They want to get bigger. So as this thing gets bigger, the volume could increase in such a way that the pressure stays the same, okay? The gas isn't being pushed down on, right? It's not free to expand as much as it wants, but we will go ahead and keep that pressure a nice constant even value. On a PV diagram, that would look like a straight line across where the pressure doesn't change its value, at all. What does change, though, and what has to change, is the volume. The only way to keep this pressure the same would be to vary the volume. If we kept this piston and we said, nah, this can't move, then what's going to happen as this thing expands is that the pressure has to increase in the system. Now, useful to us is the fact that the work, the amount that of work that this piston is going to do on its surroundings is going to be equal to that constant pressure times the change in the volume. And so that means that we can write the first law of thermodynamics, change in internal energy of the system, right? Q minus the work will be the pressure times the change in volume. So this gives predictive power. If we know that a process is occurring and we're keeping the pressure the same, then we can find out how much work this system is going to be doing on its surrounding. It's going to be that pressure times whatever change in volume the gas has. Okay? All right. Let's sort of turn the tables here, and instead of holding the pressure constant, we are going to hold the volume constant. All right. So that means that we are freezing this piston. We're like super gluing this piston into place, right? And it can't go anywhere. So tell me what the work is going to be if the volume of this gas doesn't change.
Zero.
Why is it going to be zero?
Doesn't go up or down.
It's not moving, right? Work is force times a displacement, isn't it? And so, since there is no change in shape of this gas, no change in volume of this gas, no work can be done. So in a constant volume process, the work is zero. Think of it as the change in volume is zero, and so the work's going to be zero. And that means our change in internal energy is just going to be equal to the amount of heat we put into the system. Right? It's Q minus W, but if W is zero. And what does a constant volume process look like on a graph of pressure versus volume? If constant pressure is a horizontal line and the pressure is on the vertical axis, what direction should the line be if volume is along the horizontal axis? Vertical line. So in a constant volume process, we get this vertical line. The volume never changes, but the pressure sure does, right? If we put heat into this system, that heat goes into the internal energy of the gas. And the more energy that this thing has, the more pressure it's going to exert on the sides of its container. So again, if we know that we have a situation where we are going to be keeping the volume constant, then we know that no work can be done on the surroundings, but the internal energy of that system is going to increase if we add heat, and it's going to decrease if we pull heat out of the system. There's a story almost every year somewhere in America, and the story always goes something like this. And I am going to pick on my gender because it's almost always a man that does this. But the story goes something like this. Can of food, unopened, placed on stove. For some reason, it usually is a can of beans. I don't know why, okay? Man puts canned food on stove, turn on stove. What happens? Pressure increases until can no longer contain pressure, right? Like if you put a closed container, right, on a stove and heat it up, you don't let the volume increase, right? The pressure will increase until the container fails. So what you've developed there is a bomb, a bean bomb, right? Right? Okay. Moral of the story: open can before heating, right? Okay. Like don't skip that very important step. I mean, I've cooked plenty of cans over a campfire after opening the lid, right? They're not going to blow up that way. They're just going to get warm. So yeah, watch out. Never heat your beans with the can closed. Or the glass bottle closed, right? Just don't keep things closed, right? Any of you who've ever used a pressure cooker, okay, knows that that device has safety systems on it that prevent it from exploding, right? It'll let the pressure out. That's what goes on. Anyway, okay, so constant temperature. This one's tricky, okay? Because at constant temperature, all bets are off. Both pressure and volume can change. And they change in a predictable way according to the ideal gas law. But it's not linear, first of all. Okay, it's not a linear relationship between the pressure and volume. And the amount of work that gets done in this situation, I'm not happy to report, is equal to nRT, which again looks very ideal gas law-ish, right? Okay. And then the natural log of the final volume divided by the initial volume. Like I said, it's messy, and you don't want to know where that comes from because it involves calculus. But unfortunately, the relationship between pressure and volume is not straightforward, and you end up with inverse things that get integrated, which ends up with natural logs. But there you have it. That's the amount of work that gets done. The cool thing about an isothermal process, a process that takes place at the same temperature, is that we know that the change in internal energy has to be zero. Remember, for the internal energy of a gas, right, was 3/2 nRT. And if the temperature doesn't change, then the internal energy doesn't change. And if the internal energy isn't changing, then that means that heat and work have to be the same. All right. Then we have this adiabatic process. This one's simple on the surface. In an adiabatic process, heat flow in or out of the system is zero. Think of it as like a perfectly insulated process where this system is not in contact with the rest of the universe. No energy is allowed to flow in or out. If that is the case, then all changes in internal energy either give rise to work or vice versa. Work will cause changes in internal energy. The other way that you can get Q to be equal to 0 without perfect insulation, because no insulation is perfect, there's always some transfer of energy of a system to its surroundings in the form of heat, is to do processes very fast. Extremely fast, extremely slow, or perfect insulation. Those are the ways to get adiabatic processes. And adiabatic processes actually occur in the atmosphere, in weather. Meteorologists will talk about the adiabatic expansion of clouds or air, where air gets heated, begins to rise through the atmosphere, and as it rises, it's expanding, right? It's less dense, and so it's buoyed up, and then it starts to expand because there's less pressure. And what happens is that within that rising body of air, it's not dumping any of its energy into the rest of the atmosphere. And the change in internal energy of that gas gives rise to changes in volume and work and things like that. And then eventually condensation and the formation of clouds and stuff like that. So it's a very real process. I don't want you to come away thinking, no, it can only be a perfect process. It's a very real process, but if you're going to pull it off, you have to be very careful to not exchange heat with your surroundings. And really the best ways to do that are get the insulation as good as possible, or have the process be as fast as possible. Because if you make something happen really fast, a lot of times there isn't enough time for thermal energy to get out of the way. So this is a sort of a combination graph of all four of those things that I just showed you, sort of just kind of put together in one. And it does show off the adiabatic curve, which I didn't draw for you because it can be a little bit difficult. An adiabatic curve links two isothermal curves. The temperature does change. Everything changes in adiabatic. It's just Q is equal to 0. So we've got that isochoric or constant volume process, which is the vertical one, isobaric or constant pressure, isothermal or constant temperature, and then that adiabat right there, which is where Q equals 0. I'll grab a copy of that for you so it will be in the PDF, okay? Now, we're going to come back. The whole reason we talked about those is because I want to apply them to the concept of an engine, which we're going to get to in a second. But before I can talk about engines, we do need to talk about the second law of thermodynamics. The first law is conservation of energy. That's really what it is. In terms of things like temperature and work and heat, right? It's a recasting of the first of conservation of energy. The second law of thermodynamics is unique to the science of thermodynamics. And we're going to express it three different ways for our purposes. And the first is that it's an acknowledgement that heat really is one directional when it happens naturally. By naturally, I mean that we are not, as human beings, forcing it to go the other way according to our science. What do I mean by that? Second law says that heat always flows from hot to cold. Spontaneous heat flow, natural heat flow, is always in the direction from hot to cold. So when you take your hand and you put it on, say, the window of your car when it's wintertime, right? You will feel the cold glass, right? And we often think of it of how the cold sort of seeps into us. If you've ever sat on the snow for any portion of time, you'll feel the cold sort of like, it'll just feel like cold is moving into you. But that is in fact not what is happening. What's happening instead? Heat is leaving us, right? Natural, spontaneous heat flow always happens from the hot thing to the cold thing, and never in reverse. Again, naturally, right? Allowed to follow natural law. We can force it to go the other direction by our technology. So a refrigerator is a classic example of this, right? What does a refrigerator do? Keeps things cold, right? Okay? It keeps things cold by pulling heat out of the inside of the box. That's how it does it. But a refrigerator cannot do that unless it is plugged in. I know this sounds idiotic, but it's true, right? Okay? A refrigerator cannot cause that separation of hot and cold unless it's plugged into an electrical outlet. That electricity provides the energy in the compressor. We'll talk about how refrigerators work here in a few minutes, okay? But we need that source of electrical energy to force a separation between hot and cold. And by the way, where does the hot end up? The hot that was inside your refrigerator's got to go somewhere. Where does it go? Now I know exactly how many of you have reached behind your refrigerator to clean it. Because on the back of the refrigerator, on the bottom, or maybe even the top of the refrigerator, there'll be these coils. It's where all the dust bunnies live. Okay? That's where the heat's ending. It's ending up in your kitchen. Right? So only human beings would come up with a system where to cool off our food, we put it in a box, which heats up our kitchen, which we then have to air condition because it gets too hot. Yeah. To say that we don't obey the second law of thermodynamics would be an understatement. Everybody has to obey it. It's a natural consequence of how energy flows in our universe. And to cause energy to go the other way requires us to pay a higher cost in energy to get it to happen. But spontaneous or natural heat flow always flows from hot to cold. So with that, those two ideas in mind, conservation of energy and the relationship between work, heat, and change in internal energy, and the fact that we know that natural heat flow always goes from hot to cold, we can talk about this thing in physics that we call an engine. Now, I want to be very clear. We will get into specific types of engines today, like the internal combustion engine, and the real physically engineered engines. But before we get there, I want to introduce to you the concept of an engine. This is not how to build an engine. This is the theoretical background to what an engine does. The whole idea of an engine is to get some kind of work out. We want engines to produce useful work, mechanical work that we can then capture to do other things, like move us around or run, mining equipment or push airplanes around or whatever the work is. We want some sort of kinetic energy, right, to be produced. That mechanical energy that moves things around. That's the goal of an engine. And thermodynamically, in the sense of burning fuels and all that kind of stuff, an engine's job is to take fuel and convert it into that work. All engines have some sort of energy input. We call this the hot side reservoir. It tends to be the high temperature side of the engine. So in a gasoline engine, we burn gasoline and that creates a lot of heat, okay? And then all engines have a cold side reservoir, typically called the exhaust. So you have like a energy input in the form of fuel burning to make heat. The engine then takes that heat and somehow does something. This is kind of a black box. We're not going to get into the engineering details of it. But an engine is this black box which takes fuel and heat in, converts that into work, and then whatever is left over that can't be turned into work gets pushed out of the engine as an exhaust. And we call the exhaust the cold side. I want to be very clear here though. Exhaust is generally not cold. Okay? Anybody that's ever run your car for a little while and then made the mistake of touching the tailpipe of your car knows that the exhaust is not cold. You'll burn your hand if you touch the tailpipe of your car while it's running or immediately after it's running. So even though we call this the low temperature or the low heat side of the engine, it could still be very hot as far as our human biology is concerned. Importantly, the hot side needs to be more energetic than the cold. If 10 joules of energy goes into the engine and 10 joules of exhaust comes out, how much left over do you have to do work? 0. That's a very inefficient engine, right? It hasn't captured any of that heat difference to turn it into kinetic energy. The flip side of that is that if you put 10 joules of fuel in the top and you get 10 joules of work out, that's a 100% efficient engine. It's taken all of the fuel and turned it into useful work, and there's no exhaust. The problem is, the exhaust is always in the form of heat, which we can quantify by temperature, but it's always in the form of heat. And so how do you get 0 heat? How do you get a system to have 0 internal energy? What must the temperature of that exhaust be in order for it to have 0 internal energy? Yeah, it's constant. Probably the most unforgettable constant. Not change in internal. I don't care about changes. I just want the internal energy. Internal energy 3/2 nRT from kinetic theory. What must that temperature be for the internal energy to be 0? 0. Which 0? Celsius 0 or Kelvin 0? Kelvin 0. In other words, the only way to have a 100% efficient engine is for its exhaust to have a temperature of absolute 0. Which we understand is not practically possible. Theoretically possible, but in practice, getting to absolute 0 is impossible. So that means that no engine can be 100% efficient. That's another way to think about the second law of thermodynamics. One.
So it's like the exhaust, is that like the energy that was used up to convert it into like?
No, it's just energy that couldn't be captured by the engine and turned into work.
Is there anything lost when you convert it into like, I guess, lights?
Yes, yes. So that energy lost that you're thinking about basically is the exhaust. So maybe the answer to your question was yes. There are useful forms of energy and then there are not useful forms of energy, like that our technology can't take advantage of. And usually exhaust are those forms of energy that our technology can't take advantage of. But even if, let's pretend we lived in science fiction universe where we had infinite resources and the ability to all kinds of exotic materials and all that kind of stuff, right? We can't get around the limitation that in order for an engine to be 100% efficient, the temperature of the exhaust has to be what? 0, absolute 0, right? Which is unachievable. Okay, so no 100% efficient engines. These engines, the engineering design is sort of predicted or informed by those 4 processes that I was teaching you about A thermodynamic process is going to be isobaric, isochoric, isothermal, or adiabatic. Those are the 4 things that can happen. Or, you could, but it's not just like an engine runs off one of those processes. What you want to do is you want to link those processes together, and an engine by definition goes through a cycle that gets you back where you started. You want an engine to repeat itself. It's no good for an engine to just kind of fire once and be done. What we want to get out is a sort of harmonic system that repeats itself over and over again, and we capture that work that's coming out of it in a repeated way so that we can then repeatedly move stuff, right? So a Frenchman by the name of Sadi Carnot, the Carnot cycle, he set out to figure out the best combination of these thermodynamic processes that would, A, get you back to where you started so you could repeat the process over and over again, and B, be the best, most efficient cycle that you could get. So it had to be the shortest number of steps, capturing the largest amounts of energy into work, and be repeatable, right? And again, Carnot was not out to actually invent a physical engine. He was asking the question, what is the theoretic best cycle that you can get? And this is what he discovered. If you do an isothermal expansion followed by an adiabatic expansion, so where the volume of the system is increasing, okay? And then you do an isothermal compression and an adiabatic compression, an isotherm followed by an adiabat, an isotherm followed by an adiabat, one expanding, one compressing, okay? You will get back to where you begin, and you will have the highest theoretical efficiency possible. Efficiency is a measure, okay, of the amount of work that you put into something, okay, divided by, the amount of useful thing that you want divided by its cost. Okay, so efficiency is what you want divided by what it took to get there. In the case of thermodynamic efficiency for engines, what we want is work. We are trying to get work out of our engine. And what we're paying is that fuel cost in the form of the heat energy that our fuel is providing the engine. What Carnot was able to show was that the maximum theoretical efficiency for anything, regardless of the engine's actual physical design, could never exceed the following value. And he was able to get it back to the temperatures of the exhaust and the input. So TC is the cold side, it's the exhaust temperature, and TH is the hot side temperature, the fuel temperature.
So would this be done through like, in terms of like engine, like through valves?
Okay, so we're going to actually talk about the actual physical engineering here of your car's engine in just a second. What I want to lay down is this is the absolute theoretical maximum efficiency you can get in nature. The Carnot cycle turns out to be impossible to build with our current technologies and materials. Okay, but it represents the best case scenario for engines in their theoretical framework. So efficiencies go from 0 to 1. 1 being 100%, 0 being absolutely terrible. Okay, so to get 1 here, what must be true about TC over TH? It's got to be 0, right? So again, the temperature of the exhaust has to be absolute 0, which is impossible. Okay? Any other temperature besides 0 for TC means that there's going to be some little bit of efficiency, right, that gets lost. Right? So, what does this look like in your car? Well, your car does not run on the Carnot cycle. The reason cars don't run on the Carnot cycle is because it can be very difficult to actually get an isothermal expansion to happen consistently where you're not changing temperature. It's also, the adiabat is a little bit less problematic, but it's still kind of problematic. This cycle right here, okay, is a different thermodynamic cycle. It's a different connection of the four processes that I taught you about. And it's called the Otto cycle. I love this. I love this. This was the guy's last name was Otto, O-T-T-O, but it sounds like automobile, right? A-U-T-O. But the Otto cycle, okay, is the one that actually occurs in internal combustion engines, the engines that run your car, okay? So if you have a gasoline-powered car. So in your car, right, our system consists of a piston, right, a movable part, a fuel-air mixture, a gas, right, that is going to be the system that is going to convert the gasoline into this work, right? The cylinders of the car's engine block, okay? And so what we have in your car is, this varies from car to car, but in general, right, you have a valve that allows gasoline that's been like blasted into a gaseous state, so it's liquid fuel that the carburetor in your car, the fuel injection system in your car, kind of pushes into a mist, okay? And that gets drawn into the cylinder as the piston moves down, okay? Just kind of sucks it in. And then the piston compresses, the valves close, and your car's piston compresses that fuel-air mixture. And so here, right, we are changing the volume, right? We're making the volume smaller, okay? Compressing that gas, increasing the pressure there. And at just the right time, which is controlled by other parts of your car's engine, the spark plug will put a little punk into that compressed gasoline fuel-air mixture. And when gasoline's mixture with air is just right, and you add a little spark, what's that gasoline going to do? It's going to explode. Okay? Gasoline, it's funny stuff. It's the vapor that catches fire and burns. Right? You can do not do this at home. I will not be responsible for anything that happens to you or your loved ones or your house. You can actually extinguish matches in liquid gasoline. Okay? The liquid itself, not flammable. It has to be mixed with oxygen at a certain ratio, stoichiometric ratio, for it to begin its conflagration and its deflagration. So it's usually the vapors from gasoline that catch fire. And then of course, now that there's fire, you're going to vaporize gasoline faster, the liquid's going to start evaporating faster, which adds more of that vapor to the air, which causes the, to go faster and faster and faster. Which is why the liquid eventually will catch on fire at the surface. But the whole bulk of the liquid doesn't catch on fire. Anyway, so compresses, spark fires, okay? And now that piston, right, with that exploding gasoline is going to be pushed down. It's called the power stroke. Okay? And that's the work, right, that goes to the crankshaft to help turn the transmission, turn the wheels of your car. And then, as it comes back around again, there will be a different valve that opens up to push out the exhaust. This is, again, all of the thermal energy, all of the gasoline that didn't get burned, all the byproducts of that chemical reaction, right, that's not useful anymore for the engine, gets pushed out through the exhaust valve and it goes into the exhaust system of your car to get pushed out the end. Where does the piston get the energy from to draw the gas in and compress it?
Is that the kinetic energy from the previous cycle?
So, there is some momentum here, isn't there? The car's been going for a while, and if you turn off your car, it does take a little bit of time to stop, right? So there's some momentum. So, but how does your car initially start then? The starter motor. There's a battery, and we use electrical energy to get the engine turning, right? so that this process can then start itself. Anybody that's ever tried to start their engine while it's running knows the sound of a starter motor that's very unhappy. Right? Because the starter's like, it's already running, you don't need it, right? But your car does not consist of one of these, okay? It probably has 4. There are some cars that have 3, okay? But it probably has 4, maybe 6, maybe 8, probably not 12, okay? So you have a V4, V6, V8, that number on that V, right? The V tells the shape of what the pistons are doing. And then the number tells you the number of cylinders. But so if you have 4 cylinders in your car, okay, all 4 of them are not doing this at the same time. If they did, if all 4 cylinders were exactly in step with each other, how would your car go down the road? Boom, 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 right? Like it would be this lurching motion, right? Okay, right? Lurching bad, right? Okay, not comfortable for the driver. So what they do is they offset each of the 4 to be like a quarter cycle off. So when one's doing a power stroke, the next one's doing its exhaust stroke, and the one right next to it is doing its intake stroke, and the other one doing its compression stroke. So it's getting energy from the other pistons in the system to keep this thing going, right? And it's timed correctly and all that kind of stuff. So the Otto cycle on this PV diagram, this thermodynamic process diagram, okay, turns out to be an adiabatic expansion and then some constant volume processes. Again, I know they're constant volume because they're vertical lines on the diagram, followed by an adiabatic compression and then a constant volume process. So here it's interesting, we're taking advantage of this adiabatic process, this process that's not supposed to have any heat move in or out of the cylinder. We know heat's moving in or out, like the heat of the exhaust. The exhaust is being taken care of the exhaust stroke, but your car engine just gets hot due to friction and the burning of these things. So it's not perfectly adiabatic, but it's pretty close because that power stroke happens pretty fast. Right? And all that energy, or as much energy as is possible, doesn't seep out through the engine during that fast power stroke. It's the residual leftover stuff that starts to leak all over the place. So this efficiency, right, that we're talking about when it comes to engines becomes very important because, I mean, who doesn't want to get the greatest bang for your buck, right? So let's just talk about the efficiency of internal combustion engines for just a second, okay? Modern internal combustion engines are among the most efficient engines that humanity has ever designed, okay? Internal combustion, or ICE, internal combustion engine, ICE engine, we've got 130 years of development under our belts for these kinds of engines. The engines in cars nowadays are not the most efficient designs. You can actually get designs that are more efficient than the ones we have in our mass production vehicles. It's just they're finicky, and when they break down, they break hard, and it's just not great for a consumer experience, right? You don't want to have your car's engine rebuilt every 2,000 miles kind of thing, right? So there are tricks we can play to make them more efficient, but they're not necessarily more useful on a big scale. So at scale, the internal combustion engines we have nowadays are at best like 24% efficient. Anywhere from 18% to 24% efficient. So let's put this into context, because it's important that you understand this. And in our society here in the United States of America, nobody understands anything unless we assign a dollar amount to it, right? Okay, money talks. So let's talk about the money you spend at the gas pump. And we're going to normalize this to $1, okay? So let's say you buy $1 worth of gas. And we'll just, to make the math easy, we'll say the engine in your car is 20% efficient, okay? So my question is, in terms of efficiency, for that $1 that you spent on gasoline, how many cents of that $1 goes towards moving the car? If the engine is 20% efficient, at converting the gasoline into work, then for every dollar you spend, how many cents are used to move your car? 20 cents. That's what 20% efficiency means. Where did the other 80 cents go? Out the tailpipe. Thank you. You've increased the air pollution and average temperature of fresh time. 80 cents, right? So if we can get a 40% efficient, right? That's more use out of the fuel that we are burning, right? Okay. Here's the real kicker. This is really where it hits you in the stomach, okay? Of that 20 cents, what proportion of the mass of your vehicle is you? Let's face it, it's not really important that your car get here, it's important that you get here, right? How much of the mass of the vehicle is you? Really, really small, isn't it? Okay, so in terms of useful load, right, it turns out that the amount of money that you effectively get out of that you pay $1 at the gas pump, okay, less than 1 cent of every dollar you spend is used to get you places. 19.2 of those cents is used to get your car around, because it's the majority of the mass, right? And the rest of it goes out the tailpipe.
So when we're saying efficiency, are you saying like how much you're able to move?
Yeah.
So like
The amount of work moving the car, right? Because that's what we do, right? We convert gasoline, we convert the chemical energy in the gasoline into kinetic energy of the moving vehicle.
So let's say you have like something like a Prius.
Okay.
You can go like we'll just say 10 miles, right, with a certain amount of efficiency.
Mm-hmm.
But then you have something a lot like maybe carrying a bigger load.
Mm-hmm.
Do they like offset? Like
Okay, good. You brought up the specter of hybrids. Okay, so why is the Prius and other hybrid cars like it more efficient? They are not burning gasoline part of the time. A hybrid vehicle has what else in it? Electric motors. So why does that make the car more efficient? Because electric motors, like bad ones, are about 84% efficient at converting electrical energy into kinetic energy. Now the fuel here isn't gasoline, it's electricity, right? Okay, so the electric motors in cars generally are about 90% efficient. Some electric motors are pushing 98 and 99% efficiency. Those are not the ones that they put in mass production electric cars, but there are motors that can run for a very long time that are very, very efficient. They're very expensive, but they're very, very efficient, right? But even at 84%, 85%, the worst electric motors being only that efficient, they are magnitudes more efficient than an internal combustion engine. They just are because of the laws of thermodynamics. It has nothing to do really with our engineering and everything to do with how our universe is built. So a Prius takes advantage of this increased efficiency by allowing the electric part of the car, right, to offset use of gasoline. Gasoline's there if you need it, but electricity is more efficient. Unfortunately, I don't like the Prius because I don't like the software that the Prius runs. Toyota intentionally keeps the mileage down in that car because the consumers complained that their car wasn't peppy enough, right? It didn't sound good. Shoot the consumers, right? Like, come on. We've got a lot of problems to solve, and one of them is that my car doesn't sound right. Get over it, right? Yeah.
So is Tesla worth it?
is the Tesla worth it, right? Okay, so all electric cars, Tesla or not, you got the Hyundai Ioniqs, you've got the Ford, the Chevy Bolts, right? These full electric cars, right? They are hyper efficient, like really, really efficient cars. On an everyday hit your pocketbook kind of thing, an electric car driver, like if you do all the math and convert it all and make it all the same, okay? If you're spending $1 on gasoline, the electric car driver is probably spending about 15 cents equivalent for the same mileage, same loads, all that kind of stuff, right? Okay, so the problem is with an electric car is batteries and range, okay? And this thing called range anxiety, right? Where people, the reason hybrids sell so well is people want the efficiency, but they also don't want to run out of gas, right? Or run out of electricity. Well, guess what? The electricity problem solved. There's time. Ukraine. War breaks out in Ukraine. What stopped flowing first? Gasoline or electricity? Gasoline. Why did the gasoline stop flowing first?
Needs to be physically transported.
How do you transport gasoline? Through pipes. Like the container in the ground to the thing that puts it in your car. Electricity. Without electricity, gas doesn't flow. Right? In Ukraine, electric car owners were able to move in and out of the country and through the country to deliver supplies when the gasoline supplies were unavailable. They were more reliable than gasoline cars in a situation when the electricity was gone. Because you can charge a car via solar, you can charge it via plugs when the electricity might not be able to get to the gas stations. Like there's way more gas stations for electric cars. Yes, the charge times are long if you don't have enough power, but it can still be done. That's kind of the point here, right? So it is a complete falsehood to think that gasoline is the more reliable fuel. The cool thing about gasoline, the amazing thing about gasoline is its energy density. For a gallon of gasoline, the amount of energy we can successfully extract from that is really big. It's a really, really good, useful form of energy. It poisons our air and changes the chemistry of our atmosphere to the point where we start killing ourselves, right? In terms of carbon dioxide and climate change and all that kind of stuff. So very bad things there. But in terms of energy density and safe storage and all, we've worked with it long enough, we know how to do it safely. It is a good fuel. Battery energy density is nowhere near that of gasoline energy density. And anybody that tells you about the hydrogen future is smoking dope. Because hydrogen's energy density is so bad it doesn't even belong in the same sentence as the words energy density. Okay? So all of this hydrogen, there's one exception and it might be airplanes. Okay? Because jet fuel and batteries are heavy, hydrogen is lightweight. So if we can figure out how to store very dense forms of hydrogen, we might be onto something, but that's a big what if. Okay? So that was a little bit of a tangent into this, because I know it's interesting, right? Especially as now we are transitioning into a kind of an electric car society. We really are. Okay? People are buying electric cars in numbers that have never been seen before. There seems to be been a little bit of a slowdown this year, but it's a temporary bump in the road in terms of what we've done in the last 10 years when it comes to electric car adoption. And just to be clear, I think if somebody wants to own a gas car and go vroom vroom fast, okay, by all means, do that on a track, okay? Don't do it next to my neighborhood with loud, kinds of things. But pay the price. To me, we should push that into the realm of luxury, right? And bring down the cost of efficient transportation for everybody else, right? Because if you can replace that commute back and forth to school or back and forth from your job and get it off gas onto electricity? The efficiency, just the efficiency, not air quality, right? Not the environment, just the efficient use of energy is so much better, so much better. Okay, so what's the reverse of an engine? Well, it's a refrigerator. An engine takes fuel, burns it, exhaust, work comes out. A refrigerator, the input is work. You put work into the refrigerator to cause a separation between the hot and cold sides. So in a lot of ways, a refrigerator, so theoretically, not engineering-wise, theoretically, a refrigerator is an engine running in reverse almost. Engines, we get work out. Refrigerators, we put work in to cause a separation of hot and cold. You've probably seen stickers like this if you've gone to any store that has any kind of appliance in it. You're not shopping for appliances. You probably walked past this energy guide sticker. This is the government's attempt at trying to communicate the efficiency of refrigerators. So the efficiency of a refrigerator is called the coefficient of performance. Again, efficiency is always what you want divided by what you pay, right? In the case of a refrigerator, what we want is Q cold. We want that cold side, and then what we put in is work, right? So it's Q cold divided by work for the coefficient of performance. But again, because Americans don't understand science, they do understand, well, but Americans don't understand economics either, but they do understand dollar signs, right? This label is trying to communicate not the actual cost, but a relative cost. If you look at this label and you buy this thing and you're going to think that this refrigerator is going to cost you $67 a year to run, that's not what this is saying, okay? But if you're looking at one refrigerator and it says $67, and the next one costs $80. Those are the actual things you're going to pay, but it is communicating that the one that costs $80 is less efficient, right? It requires more money to run, right? So as a comparison between appliances, this is actually fairly useful, but as an indicator of what you will actually pay, it's not useful at all. Because what you actually pay for electricity is completely dependent on where you live. A bunch of other factors, okay? So do realize, right, that these labels are misleading in that one sense. This isn't what you're going to pay. It does not cost $67 a year to run a refrigerator. Could cost more, could cost less. But if there's another refrigerator there that has the $40 on it, okay, it will over time cost you less than the one that, okay. So how do refrigerators do it? It's taking advantage of the fact that when you compress or expand a gas, it will cool off or heat up. And so if we can get, right, high pressure gas to condense on the outside and then expand, that expansion causes it to be cold, and we can, that cold, right, second law of thermodynamics, heat always moves from hot things to cold things. If we keep the cold side inside the insulated box, then anything warm you put in there will cool off. That heat will be drawn out as the evaporator side, okay, expands, and then it gets recompressed. This is where the work going into the system happens. This compressor runs via electricity. When you are sitting there and it's kind of quiet in the kitchen, and then all of a sudden you hear that click, and then the refrigerator starts buzzing, that's the compressor working, right? It's spinning, it's a little electric motor down in there, and it's compressing that gas, okay? And trying to get that high pressure side and dump that heat out into the kitchen area, okay? And then use the cold side to pull the heat out of the food that you happen to put in there. Refrigerators are nice, but they're only cold on the inside and hot on the outside. An air conditioner is a house-sized refrigerator, isn't it? Only very, very important, where do we put the hot side? outside, okay, right? So if you have an air conditioner on your house, you probably have like either up on the roof or maybe on the ground next to the house. There'll be that condenser, sometimes it's called. It's a big fan that makes big buzzy noises while the air conditioner is going, okay? That's the hot side of your air conditioner. The cool side is somewhere inside your house, probably close to the furnace. The furnace doesn't run, but the refrigerator's evaporator coils are on the same out, because the furnace is the blower that moves the air. It's just, it doesn't turn the hot side on while it's in this mode. And so cold air is moved throughout the house, right? Whereas hot air is pushed to the outside. A lot of times these devices, well, in physics we call them heat pumps. We don't really call them refrigerators. Call them heat pumps because you're literally extracting heat from one area and pumping it to another spot. Usually against the second law of thermodynamics. You need input energy into this system in order to cause this to happen. The term heat pump is becoming more and more popular, especially here in the state of California, because gas furnaces were outlawed 4 years ago for new installations. If the furnace goes out in your house now, you are not allowed to install a gas furnace back into the house. The reason the state of California did that is, again, because fossil fuels and natural gas leaks in attics are very bad news, safety and all that kind of stuff. Those of us who are skeptical and cynical will also say it was the heat pump lobby that got it. Anyway, what you can put in is a heat pump. Heat pump is an air conditioner that can flip itself. So an air conditioner makes sure that it pumps hot to the outside during the summertime, right? A heat pump has a special valve in it that can reverse the flow of these things, so that the hot side becomes the cold side and the cold side becomes the hot side. So in the winter time, if you want hot air in your house, you run the air conditioner, you run the heat pump in reverse. So that the heat pumps cold, you try to cool down the outside, and then where does the hot heat get pumped to? Inside your house. So in the wintertime, that's what happens. You're trying to cool off the cold air, right? And in the summertime, you're trying to heat up the hot air that's outside and the cold side. They are very efficient. A friend of mine is a salesperson. He sells water heaters that are heat pumps. And his company specializes in doing this in areas where low-income families tend to live. They get government subsidies because the heat pumps are kind of expensive. So it's a subsidized cost for the heat pump, which makes it on par with a standard electric or gas-fired water heater. They can then go in and install that, and that low-income family will pay less money to actually operate the hot water heater because heat pumps are way more efficient than a gas-fired furnace. And they're actually more efficient than, even though they're very, very closely related to an air conditioner, they tend to be a little bit more efficient than air conditioners. It's really weird. I got a heat pump installed in my house about 6 years ago, and I had to rewire my brain as far as running the air conditioner was concerned. Because as a dad, dads are always about turning the lights off and it's costing me money, so just suffer. It'll be good for your character, all that kind of stuff, right? I went from basically running the fine edge between my family dying and spending money, right, to cool the house off, to run the darn thing all the time. Because heat pumps, they can't cool things off very fast. They need time to kind of move that energy around, right? And so you run a heat pump almost 24/7. The heat pump will change, unlike an air conditioner, which is on or off, it's either just cooling the air off to a certain temperature or it's not. A heat pump can actually, it goes through these almost infinite number of stages of cooling. And so what a heat pump will do is it'll cool the house down, and then it will just sort of maintain that temperature by just running all the time, but at a way more efficient setting. So like I said, I had to really kind of recalibrate my brain. Because As a homeowner, anytime the air was moving, like, do you hear that sound right now? Do you hear the running of the fan? That's money, right? And so now I hear that sound quite often in my house, and it's not money because it's so efficient. It's like we're paying less running the air conditioner now than we ever have before, and we run it more. Who knew? So the second law of thermodynamics, okay? It's at its base level, spontaneous heat flow, natural heat flow, not human influence, changes of energy, always go from hot to cold. But another way to think about it is in this idea of engines and efficiency. And so another way to think about the second law of thermodynamics is that a 100% efficient engine is impossible. You can get close, but it really is impossible. So there's a third way to talk about the second law of thermodynamics. And it involves a word that if you've had chemistry, you were probably tortured with for too long. And that word is entropy. I'm just looking for the faces of horror as I mentioned the E word. What was entropy? What's entropy? Everybody's kind of heard it a little bit. Even if you have any chemistry.
Unpredictable randomness over time.
It's disorder. It's a measure of disorder of a system. What is that? Disorder of a system.
Things fall apart.
Yeah. The example I like to use is of your room, right? So I don't know what your living situation is, but let's just say you live in a room, okay, by yourself. You can clean that room up, right? And it takes a lot of energy and concentration and organization to get the dirty clothes put in the hamper and the papers all stacked and all, right, okay? And it feels like you could leave your room, seal it with duct tape and not let anybody in, and when you get back into the room, the dirty clothes will be on the floor and the papers will be spread all over the place and it'll just be a mess, right? In nature, systems tend toward disorganization. They just naturally fall apart, right? Okay? It takes energy and input of work to reorganize that. A more thermodynamic example would be putting ice in your drink. Okay? Ice in water, or a drink or soda or anything like that, is a very low entropy system because the cold molecules are in the ice and the warm molecules are in the water. But if we just let it sit there, what happens to the ice? It melts, right? And the molecules that were cold, that were in the ice, get dispersed into the molecules and it gets all mixed up. And so when the ice has melted, we would say that that system now has a higher entropy. The molecules of cold got mixed in with the molecules of heat, and they transferred all their energy and did all that thermodynamics, but now it's all messy, it's all mixed up. And in order to get the exact molecules that were in those ice cubes back into those ice cubes is impossible. Like, that's not possible. Little tiny molecular tweezers. Oh, you were the one that was in the ice. I'll put you over, right? It's just stupid, right? Now, can we turn some of the water back into ice? Like exact mass? Sure, we can put it in a refrigerator and freeze it. But again, even that takes more work than just letting the ice melt. Entropy is a way of keeping track of how organized and disorganized systems are. The reason I'm talking about it is because the different kinds of energy, some of which we've talked about in this class, have different amounts of entropy associated with their states. And what I've done here, okay, is I've given, this is not to scale, but it's implying a scale, and I've given an order, okay, from the most useful form of energy at the top to the least useful form of energy at the bottom. And by mechanical energy, I mean both kinetic energy, gravitational potential energy, spring potential energy, those are all mechanical energy. The energies we have studied in this class, except for thermodynamics, have all been mechanical energy. We've been studying thermodynamics in this last unit, so that's the thermal energy. You see it's at the very bottom of the list here, isn't it? Okay. And then we've got some other energies that I just put on there for reference that you'll be studying in Physics 2B if you have to take that class. Okay? So let's go through it. So I said usefulness. The usefulness of energy corresponds to our ability to use it to do stuff. That's why mechanical energy is the most useful. The energy of motion, the energy of position, the energy stored in a spring or the gravitational field, those are all highly useful forms of energy for us as human beings in our technology. Thermal energy turns out to be one of the least useful, which is weird because, like, notice how thermal energy is always associated with exhaust. Chemical energy. Let's go back to car engines. Okay? We are burning gasoline. Gasoline stores potential energy in the chemical bonds of the gasoline molecule. Car's engine is designed to liberate that potential energy stored in those chemical bonds and turn it into what kind of energy? Mechanical. The whole point of a car is to get it to go places, right? So we are taking chemical energy and turning it into mechanical energy. In this visual representation, chemical is lower than mechanical. So in the conversion of chemical to mechanical, we pay a huge price in thermal. Moving up, okay, means that we end up paying large prices. So the further apart two kinds of energy are on this chart, the more you pay in terms of exhaust and efficiencies. But in the terms of second law of thermodynamics, we end up with a lot of disorganized thermal energy that, quite frankly, we can't use. Another way to put this is, when was the last time you saw a car going down the street running on air temperature? Like, that doesn't happen. We can't capture the exhaust of our cars and then use it to move another car. It is literally energy that we can't do anything with. Theoretically, I suppose you could cook a hot dog with it, but that right? Okay? That's just heat moving in from one object to another. We can't turn it back into mechanical energy. It is lost to mechanical energy. Notice that electrical energy is closest to mechanical energy. This is, again, why electric motors are more efficient than gas motors. It's a closer step. Electrical is so close to mechanical that we can get those really high efficiencies. Do we pay a price in thermal energy? Do electric motors heat up? Yes, they do, right? But the amount of thermal energy that comes off is much less. Entropy in chemistry, they keep track of the entropy of systems and blah, 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 blah. In physics, for us, it's more about how useful is that energy and what price do we pay for using that energy. And so another way to think about the second law of thermodynamics is that we always pay a price. As soon as we try to organize something, take it from a state of disorder and put it together into a state of order, whether that's building a road, building a house, eating a candy bar. That's an organizational process. We're taking the calories from our food and we're turning them into cells and energy and ATP and ADP and blah, 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 right? Okay? That's an organization. But we always pay a price in disorganization, in waste, in energy that we can't use. And so it's almost like we are kind of always losing, right? The entropy of the increase of the universe always increases. In perfect processes, theoretically, it could stay the same. but it certainly doesn't decrease. If you see a decrease in entropy in a system, it's guaranteed that somewhere else paid a price of much higher disorder. But the good news is, no matter what, you're always going to be on the winning side. Because entropy always wins. Congratulations. You made it to the end of Physics 2A lecture. That is an accomplishment, right? I will see you, not tomorrow in grass, because I won't be there. Remember, grass opens at 8 for those of you that come early, right? The door won't open till 8. And on Tuesday, we will review for all of this thermodynamic stuff, and I will get the topics for the exam posted as soon as I can this morning. Have a great rest of the day.
What was the chapter called?